Good morning, my favorite and diligent student, the only one who is actually listening me monologuing and speaking about these lectures. So this lecture is really focused in educating you and just you, nobody else. So the course is still laser physics. It's about photon lifetime and cavity Q factor that we will be lecturing to you. And as the name suggests, we are really covering dynamic aspects of a laser resonator. So we are really interested in understanding how the photon lifetime evolves in a cavity. So essentially how it can decay inside the laser resonator. And then we will define a cavity Q factor as a useful parameter of understanding how the dynamics actually go. And I would like to point out that in the previous lectures, we have been talking about the cavity finesse, F, as a parameter that tells something about the line width sharpness. So of course, this cavity Q factor is also a parameter that tells something about the line width of the resonator. So in a way, finesse and the Q factor are very much related parameters of a system. So basically of a resonator. But they have a little bit of different kind of perspective on things. So in a way, finesse also is related to the free spectral range of your resonator, and the Q factor really only says something about an individual peak. So there's the kind of a main difference between these two parameters. So they are telling about the same thing about the kind of photon lifetime inside the cavity, but nevertheless the focus is slightly different regarding the use of these two different parameters. So finesse and cavity Q factor. But let's get now started. I will want to be highlighting to you that we will next study the temporal dynamics and the properties of a laser resonator. And basically, why do we care is that this is the physics that dictates, for example, the line width of a realized laser. So if you would want to realize a narrow line width laser, which of course obviously has implications on the coherence properties. So if you have a kind of narrower line width laser, then the temporal coherence is superior to a case where we have a broader line width laser. So in certain applications, these kind of narrow line width lasers are the lasers we want to make and we want to use to do our research and of course use them in the applications. So that's the kind of motivation here. We want to understand how the line width is being formed and how can we tweak the line width of a realized laser. And what matters here is that essentially it's really about the kind of cavity geometry and the cavity properties. So if you look at the figure here, we can see that in all its simplicity, the cavity can be formed by using two mirrors, placing a gain media inside, and then have kind of external components there. For example, this kind of Brewster plate, exemplifying that there are some kind of other devices or mechanisms that give rise to losses within the resonator. So one loss mechanism, of course, is the reflectivity of mirrors, and in a way we always need to have a kind of a little bit unideally here, so that we need to be able to have a non-unity reflectivity rho for one of these mirrors so that we can actually couple light within the cavity. And on the other hand, we also, if you want to make a laser, we want to also have some kind of output coupling mirror that couples actually light out. So most of the time when we want to make light sources, we are not just interested in the field inside the cavity, but rather what is the output of the cavity. And these dotted arrows here, what I was drawing into this figure, they are trying to exemplify that there are other loss mechanisms within the cavity, and those are sometimes used to describe using this kind of Li or Lint internal loss parameter that describes what kind of losses you have in a cavity. L here is the length of the cavity, and basically rho 1 and rho 2 are the mirror reflectivities. And we are interested in kind of round trip within this kind of laser cavity or resonator. So the round trip intensity I, basically looking at the kind of picture can be given that the intensity after a round trip will be the original intensity when we start the round trip. So that would be our kind of starting point intensity. And now what happens is that we will have the mirror reflectivities playing a role. So they are reducing the intensity. And of course we do have the internal losses, and basically the internal losses are being calculated twice. So they are associated with a kind of like 1 L length propagation through the resonator. So when we have 2 passes in a round trip, we are multiplying that factor with a power of 2. So Li is the internal losses, whatever like is the kind of physical originator of those losses that kind of comes into play in this description. So it could be, for example, a kind of like absorption losses due to the gain medium. It could be this kind of like scattering of dust particles and whatnot. It could be a Brewster plate placed there acting as an etalon, so to further narrow the line width of the laser, and all of those things would give rise to additional internal losses. Now, please note these reflections from the optical components, like I already mentioned, cause also internal losses. So please remember this. Now, the round trip time RT is given by the speed of light, c, divided by 2 times L, assuming that we just have a kind of like air or vacuum within which we are having the light propagating. Of course, this would need to be modified if you would have something else here. So naturally, for example, this Brewster plate actually would need to be taken into account here. Maybe the easiest means would be to tweak the length of the cavity to be an effective length of the cavity, and then this equation could be used as such. So that's the round trip, and we are now interested in calculating what kind of number of photons in the cavity do we have. So phi, what happens for the phi parameter, and why do we care is that this parameter is proportional to the intensity of the field inside the cavity. And we want to look into the temporal dynamics of this intensity within the cavity. So this is the kind of premise what we are doing next. So the photon number 5 follows the same functional form as the irradiance or intensity. If we loosely misname irradiance as an intensity, phi equals to the original phi before the round trip, phi naught times the mirror reflectivities, ρ1 and ρ2, times the internal losses to the power of 2, due to the fact that we are propagating through the cavity 2 times to make a round trip. So this is the number of photons after a first round trip. And then after m round trips, we will have a kind of modified number of photons. And here, with this, I mean in a parenthesis that after m round trips, the number of photons is given like this. So basically, it's just the same math as before, but now we are multiplying that to the power of m to get m round trips. And now we're interested in looking at the limit, that what happens when we are really letting m to go into infinity. So after infinitely long round trips, what will be the photon number? So essentially, we are interested in calculating this kind of limit. We can take the limit out of this term here, and we just let the m go to infinity. So we basically get an exponent out of that. So basically, we have something like this. So it's essentially a decaying function of like a time t over tau c, that is the effective lifetime, photon cavity lifetime, that we need to now figure out what that actually is. So it's something depending of this kind of term plus something additional. So this is the limit where m goes to infinity, and now we want to calculate how do we actually like calculate that tau c. So for an infinite multiple, so m tends to infinity of round trips, we can really calculate now the photon number decay time. So that would be the tau c of the cavity through the above expression, by just noting that now in the previous slide we did have an equation for the round trip, and of course after m round trips the total time that has passed is basically the number of round trips times the time it takes for a single round trip to make. So that would be the c over 2l here. So we solve that equation for m and we substitute that into the above equation, and what we get is that there we get an expression for the cavity decay lifetime. So tau c equals to 2 times L divided by c. So that would be the single round trip time. And then we have that natural logarithm of the mirror reflectivities, ρ1, ρ2 times the internal loss term like this. So this is the photon cavity lifetime that basically tells us now how photon number, or in other words, the irradiance within the cavity decays as a function of time. So you can now plug tau c into this equation, and we can now really describe the photon number evolution or intensity evolution easily using a simple equation. So that's where we wanted to go. And now let's start heading towards the definition of the cavity Q factor and what's the kind of physical meaning of the Q factor. So decay time tau c corresponds physically to the average time a photon spends within the cavity before it leaves out from the cavity. So that's the kind of like physical meaning of the tau c photon cavity lifetime. Please note, since the number of photons phi in the cavity decays, so does the field intensity and so does the electric field parameters decay. So basically we could write for the electric field that it would be of this kind of functional form. So we have also the electric field decaying, and it's at the same time, of course, it's oscillating at the optical frequency omega here. So this is the kind of like how the field then evolves within the cavity. And looking at this simple equation, we can see that the Lorentzian line width of the frequency can be also defined as the inverse of the cavity lifetime. So basically we can see that the kind of like a frequency line width is proportional to the inverse of tau. And how do we see that? Is that we take a Fourier transform of this guy, and we can then describe how does that field look in the frequency spectrum, and from there we can calculate that the line width actually depends on the tau c parameter. Now we can use this to define a new parameter, so the Q factor, and that's an important parameter for a cavity or a resonator. So essentially a very important parameter to describe the temporal behavior of a resonator is known as the quality factor, usually abbreviated as the Q factor. And this is really defined physically, that Q equals to the oscillation frequency and times energy stored within the cavity divided by the energy loss. So the energy stored physically, of course, that's basically the number of photons within the cavity. So that's proportional to the number of photons 5. And we have the functional form for the photon number just derived. And now the energy loss is essentially, if you think about the physics, it's the number of photons that leave the cavity within a time interval. So basically that would be the time derivative of the photon number. So now we can plug these into the definition of the Q factor. So we have something like this as an equation, and what we are left is that we need to be calculating what is this time derivative of the photon number, so that we can actually have some kind of more easy to use to estimate things and use in equations. So this is the kind of end outcome of our calculation. And why do we get into this is that we can calculate the time derivative. So that basically is the equal of a original phi times the time derivative of this exponential decay term. So that's basically just a mindless time derivation of this. And what we get out from here is that it's basically phi naught divided by tau c times the original exponential decay term. And from here, simplifying things, what we get is that we basically can write that using the original time-dependent phi, the photon number. So it's something like that, and that we can readily change into the form that's basically the kind of like a line width of the Lorentzian oscillator, like that. And now we can plug this guy into here, and then we end up with this equation. So that's how do we get rid of this phi that we originally had in the denominator. And please note that for the Q factor, we can many times just use this kind of approximation. So the Q factor was just calculated to be something like this. So we can pretty much approximate that it's it's omega naught times the tau c. So that's basically what we can do and use. The quality factor is proportional to the cavity lifetime. So this is what we just saw or see in the previous math we just stumbled upon. And what this means physically, that if we would want to adjust the Q factor of our resonator, of course, we could just adjust the mirror reflectivities, so those ρ1 and ρ2 terms. So the higher these mirror reflectivities would be, the longer the photon would stay within the cavity, and of course, the higher the Q factor would be. Physically, what this also means, if we recall the physical definition of the Q factor, we just outlined to you. So essentially, it's a ratio of energy stored with respect to the energy loss. So if we have a higher Q factor, then we also have a resonator where we have more energy stored within the resonator. So that's the kind of physical motivation for looking into this kind of high Q factor resonators and high Q factor cavities. So essentially, if we have a higher Q factor, then we have a possibility of storing a larger amount of optical energy within the resonator. So that's the motivation for these kind of resonators. The longer the photon stays within the cavity, the longer it can also participate in the amplification process. So this is the other advantage of working with resonators. So the light matter interactions can be increased greatly if we are looking at things or looking at the time light matter interaction within the time domain description. And this is actually extremely useful because this, for example, contributes now very favorably to the lasing action. So we can more efficiently pump the gain medium, and we can more efficiently, more easily have the laser resonator to actually start oscillation. So actually start having a gain into the signal lasing wavelength. And this gives us a few design tips or one design tip for a kind of as a kind of a rule of thumb to think what kind of laser cavities, laser resonators one would want to design. So a cavity should have or must have the highest possible Q factor that you can attain. So that's a good kind of design rule for you. Unless you want to work with some kind of broadband lasers or mode-locked lasers and such. So basically ultra-fast lasers where it's not simply about the Q factor of your laser resonator anymore, but something else also comes into play. But more on that in the upcoming courses on laser technologies. And now I will end up the lecture by asking a kind of discussion related question. So how the Q factor of the cavity affects the output of the laser. So this is now a surprise to you. We have been discussing a lot about the Q factor and just mentioned that the higher the Q factor is better. But now if we would want to really use the output power of our laser as a kind of some kind of metric for telling is the laser good or bad, then I really recommend you to think about this and find some kind of answer when we are meeting on campus or remotely, that how this actually starts affecting things. And I must say that they spoil a little bit of the fun already for you figuring out, but it's not exactly trivial dependence anymore when we are looking also at the kind of output power of a laser. But I will let you think about it, and we will talk more later when we are meeting. And now I'm done with this lecture. I'm done with the chapter 3 lectures. I hope you have enjoyed the ride so far, and please join me quickly when we are starting the lecture about the chapter 4, which is the last chapter we have in our course on laser physics. So thank you and good night.